Each year, more and more fragrances hit the stores, with the best-selling perfume raking in around 5 to 20 times more than a movie blockbuster. You can understand why celebrities and fashion giants have cashed into it. But hidden in the art of perfume making is the science behind fragrances. Perfume has been around for millennia. Carvings from ancient Egypt show women making lily perfume. And in the 18th century, Louis XV's court was soon renamed La Cour Parfumée, the perfumed court, due to his insistence on having fragranced rooms. However, it was one man's discovery that revolutionised the perfume industry. In 1868, William Perkin, who had already given the world the first artificial mauve dye, synthetically altered the structure of an organic compound found in tonka beans. The result? The smell of freshly cut hay, which he called coumarin. With the ability to now create synthetic molecules, the perfume industry moved out of the garden and into the laboratory. Synthetic molecules allow for longer-lasting fragrances to be made that could be produced in greater quantities. It opened up endless possibilities, creating an art out of perfume design. With the talent of creating exquisite fragrances just from his natural ability as a nose, I've been sent to Neil Morris Fragrances in Boston to sniff out the secret behind perfume design.
I'm going to show you a scent that you will readily recognize, I'm sure, but also does not, it would exist in nature, but this has been created as an art essence.
Wow, strong chocolate. Wow.
Very strong. Now there are, you can get Cocoa Absolute, which smells absolutely wonderful, but also it does exist as an art essence too.
As a chocoholic, that sniff of cocoa gave me a tingly feeling all over. However, I had to fight back my craving and get down to some more serious work. Luckily for me, I wasn't wearing any perfume, so my skin could behave as a blank canvas for Neil to create a new fragrance just for me. He began by asking me a series of questions to find out more about my tastes and personality.
Well, let me ask you, if you had the choice, would you walk to the woods, walk on the beach, or walk to a field of flowers?
The beach.
Okay. So immediately I'm going to bring down a scent here, and let me ask you what your favorite color is.
Now this is hard, I've got two. Pink and purple.
Pink and purple?
Yeah. As Neil was asking me these questions, he pulled down a series of bottles containing scents that had been created synthetically, something Neil prefers to call art essences. These particular scents were then categorised into top notes, middle notes and base notes.
Okay, so we're going to start with the base notes. You said the beach, correct?
Yes, the beach.
Okay, now this is an oceanic note.
Yeah, it's really clean.
Isn't it?
Yeah.
Okay, and now we're going to move to the two middle notes.
So you've talked about top notes and middle notes and base notes, but what does all that mean?
Some fragrances are linear, which means when you spray them on, they smell the same from the moment you put them on until the moment they disappear. But most fragrances, and the ones that I like the most, have top, middle, and base notes. So
just like a violin in an orchestra, the top notes are the scents you perceive first. They are high and light. Then comes the body of the perfume, the middle notes, which are also known as the heart notes and represent the cellos. Lastly, we smell the base notes, the scents that hold everything together and linger on the body long after the top notes have dissipated, much like the double bass. So this smells amazing. How would you describe this whole fragrance then, that's been made up of all these different scents?
How would I describe it?
Yeah.
Well, I would describe it as a warm floral.
A warm floral?
Yes, with some definitely fresh overtones. How would you describe it? You have a nose.
But is my nose smelling the same as your nose?
Well, nobody really knows.
That last response from Neil got me thinking. Even if we don't smell exactly the same thing, there must be something fundamental about the scent that makes it convey a certain smell to our brain. So what is it about the scents that allows our nose to differentiate one smell from another? It's funny, I'm doing all this research to try and figure out just how we as humans smell. but there's nothing that kind of stands out there saying this is the mechanism behind how humans smell. So it's actually doesn't seem like we necessarily fully know. I mean, the general consensus among the scientific community is that it's a lock and key mechanism. So each scent molecule has a specific shape, and that binds to a specific receptor. And these receptors we evolved to have, which then means how can we smell the things that we didn't evolve with, such as gasoline, that we didn't have billions of years ago. But I've come across this name, Luca Turin. He actually has a different theory. He believes in something known as the vibration theory, and that's basically each molecule has a certain vibration, and it's this vibration that gives it its characteristic scent. I decided to track down Luca Turin so I could find out more about his vibration theory as well as his view on the lock and key theory.
The idea that smell works by lock and key is the most reasonable idea. It's based on the fact that almost everything else in biology, enzymes, antibodies, drugs, etc., work by lock and key. The proteins that we're made of recognize and act upon smaller molecules like smells or drugs or parts of our metabolism by binding to them with a complementarity of shape, just like a lock and a key. You would expect there to be a correlation between the shape of molecules and their smell. And actually, it's an absolutely terrible correlation. And there's many ways of showing this.
One such example being the test with methyl alcohol and methyl sulfide. They both have similar shapes, the only difference being one has a hydrogen atom attached to an oxygen, whilst the other has a hydrogen attached to a sulfur. If the lock and key theory worked, one would expect the two molecules to smell the same, but they don't. In fact, the sulfide smells like rotten eggs. The vibration theory says our nose detects smells through molecules' vibrations. So if we take the examples of methyl alcohol and methyl sulfide, we'd expect them to have different vibrations, and that's exactly what we detect. To further support this theory, Luca found molecules such as borane that has a similar smell and vibration to methyl sulfide, and yet has a very different shape.
But how does it work?
Yeah.
Right? Because the machines that we use to detect molecular vibrations are big machines, the size of a fridge, and they're full of optics, mirrors, gratings, photomultipliers, all that stuff. If you look up somebody's nose, you don't see any such thing. And therefore, the reaction to Malcolm Dyson's theory, and also to, much later, to Bob Wright in the 50s and 60s, was always terrific. How can we make this work with biology? So that's what I contributed. If you start thinking of an electronic device that could detect vibrations, things are quite different, because there are perfectly good, nanoscale, tiny little electronic devices that can detect molecular vibrations using a process called inelastic tunneling.
During inelastic tunneling, the electrons start off at a higher energy level than the level they wish to reach. In order for the electrons to cross the vacuum and reach the lower level, they must lose some energy. If the molecule which is in the detector has a vibration that matches exactly this energy difference, then the electron can tunnel across. This flow of electrons can only be switched on when the molecules with the very specific vibration are present.
So basically what you have is a device which acts as a switch that detects the presence of a particular vibration in the molecule.
With taste, sight and hearing all relying on vibration, it does seem plausible for smell to work in a similar way. However, in spite of this possible unity across the senses, the vibration theory is still rather controversial within the scientific community, who believe the theory still needs further validation. It's been almost 150 years since William Perkin revolutionised the way we make perfume. And whereas we understand a lot about hearing, sight and taste, the biological explanation of smell is still eluding scientists, making it the last understood sense.